So today's video involves numerical integration. That sounds scary at first, but you've actually already done this if you've taken a calculus sequence. Because a numerical integration is really nothing more than computerized Riemann sums. You might remember Riemann sums. You use this when you were getting the formal definition of the integral. You want to find the area under a curve, so you divide it up into rectangular strips, and more strips is better. The more strips you put in, the less of these gaps you have between the actual area and the rectangular area, and so your error in the area estimation goes down. Now you probably, if your calculus class was like the one I took, you probably blitzed through Riemann sums to get to the real integrals. Well, unfortunately, it turns out you can't actually do a real integral on a whole lot of functions, especially the ones you encounter in physics. And so in order to do most integrals, you have to put them into a computer and get a numerical answer. And the way you do that is with these Riemann sums. So as a reminder, these strips have a width of delta x. We're going to call that dx in the code because I get tired of typing out delta all the time. The thinner you make the strips, the smaller the dx, the better your answer is going to be. Let's take a look at a simple example of how this works out. So in this code, we're defining a function called integrate. We're going to integrate over a certain range with a step size of dx, with a stripped width dx. So we're going to integrate this from x min to x max. We're going to create an x array and a y array. Our x array is going to be all of the x values that we're interested in visiting. That's going to go from x min to x max in steps of dx. And our y array is just going to be all the values of f that we need. We're going to define f down below in just a second. This is just to set up the interactive machinery that we need for this activity. Then we're going to just calculate the area. We're going to use the trapezoidal rule. You might remember the trapezoidal rule from your Riemann sums. The idea of the trapezoidal rule is that you've got your function here you're interested in integrating. And instead of making rectangular strips, you're actually going to make trapezoidal strips. So you're going to divide this up into these points like this. Let's get this going up higher here. There we go. And what you're doing is creating these strips to have an angled top so that you're actually kind of following along the curve here with a straight line going in between there. That's the idea of the trapezoidal rule. Mathematically, the way it works is you take the sum of all the values, subtract off half of the endpoints, because basically each of these points is going to get counted twice. Once for this strip, and then once for this strip, once for this strip, and once for this strip, once for this strip, once for this strip, except for your two endpoints, right? Those are only going to get counted once for this strip and for this strip. And so the net result is all of this stuff here. And then we have to multiply by dx, because in order to get the area, we've got to multiply by dx here. And it's that multiplying by dx that takes care of how when you make smaller strips, you're getting more strips. And so that's sort of balancing the fact that you're actually adding up more things when you make it smaller. And then we're going to create a graph. We're going to create a graph of the actual function, and then we're going to show you what the area looks like to give you an idea of how good that approximation comes out. The other thing we're going to do is define something called interactive plot. This is going to create a set of widgets for us where you can actually specify what the range is for x min and x max and what the dx is. This doesn't actually create it yet. We actually have to call interactive plot on the next cell. This is just telling us that we are ready to go. Next, we're going to define our function. This can be anything you want. Let's start out with a simple one. Let's start out with a nice, simple x squared. We'll come back to this more fun one in a second. Let's start out with x squared. So set this to be whatever function you want. This could be a polynomial. This could be a trig function. This could be an exponential. Literally any function you want, you can numerically integrate. We define the function here, just set it equal to y here, and then we're going to create our interactive plot. Pause for cough. So here's our sliders. Notice that you have two controls. You have your x range and you have your dx. Let's just work with the default for right now to get an idea of how good of an approximation this is. We are calculating the integral of x squared dx from -1 to 1. I know from Calc 2 that the answer to this is 1/3 x cubed right? So think of it as the reverse of the derivative. If you were to take the derivative of this, you would drop the 3 down here. That would cancel out with this 3 because there's no fraction out in front here. Then you would demote this 3 to a 2, would give you x squared. Hooray, that works. I'm not going to worry about adding the plus c because this is a definite integral. The c would just cancel anyway. So we're going to take a -1 to a 1. By the way, one of the reasons your physics professors are probably likely to forget the plus c is because we almost always work with definite integrals. It's very rare in physics to work with an indefinite integral. Just a little tidbit for you there. So the way this answer should come out, it should come out to be 1/3 and then an x cubed evaluated at 1 minus an x cubed evaluated at -1. So I'm going to have a 1 cubed minus a -1 cubed. Please keep track of your minus signs on these things and don't trust Excel to keep track of those because it does not do the order of operations correctly. All right, I got a 1/3 here, so I'll have a 1 cubed gives me 1. -1 cubed gives me -1. I am subtracting a -1. If you've never seen this trick, when you are subtracting a negative, you flip one of the negative signs and it becomes a positive sign. So we have a +1 here. So all of that worked to get me a nice simple 2/3. So this should be approximately 0.66, repeating, we'll round it off to a 7 there. So I'm expecting a result of 0.667. I get an answer of 0.69. How far off is that? We'll take a 0.69 minus 2/3. We'll use the full-fledged answer. Divide it by the actual answer of 2/3. Multiply by 100 to get a percentage. I'm off by 3.5%. That's not terrible. It's not great, though. So, I could do better. Let's see what happens to that result when we decrease the step size. Remember, anytime you want something to get better in a code like this, you want to decrease the step size. So let's decrease it here. You notice that every time I make a change to these sliders, the graph, the calculation is going to automatically update. Because whenever I update something with these sliders, it's automatically going to rerun the function that we defined earlier. Let me get that circle back over there. Now I've got a 0.74. Oh dear, that actually got worse. We probably have to get even lower. Okay, now we're down to a 0.67. We had an issue there with the endpoints. It wasn't quite getting the endpoints there. What I want you to notice is that as we decrease this, this is generally going to get better depending on where our endpoints lie. Let's actually increase the number of digits that is showing. Let's see, strength round area 2. Yeah, let's make that a 4 here. So we'll redo this. And we'll redo this. You can feel free to tweak that code as much as you need to. You can always change it to suit whatever your needs are. Yeah, so what you'll see is we're getting close to this point. Oh, there we got it exactly. We're generally getting close to this 0.666 repeating. There we've probably going to get it as good as we're going to get. What you'll also notice is that the quality is going to level out, right? I'm not going to get any better than this. I could show more digits if I want to, but I'm getting less payoff for my dx here. And so you eventually reach where you say, okay, this is small enough. I'm good enough in terms of my accuracy. So this is the control of your accuracy. The other thing I want you to notice as we decrease that is that this graph got a lot smoother, right? So if I put this back up to its original place up here, up here, you notice the graph is a lot more jagged because you have fewer points. Because remember, this connected line graph, very few points here, because what you're doing here is you're saying I want to connect each of these points together with a line for the display, but I'm really only evaluating here at the corner. So this is where I'm getting my trapezoid, right? So each of these is the trapezoid that I'm looking at. And so the smaller you make dx, the smoother the curve is, and the better your integration result is. So you always want to think in terms of making the graph smoother. Ooh, look at that nice smooth parabola we had there. And we're only off by 0.0001 now. Or 0.0001 and some change, yeah. You can also change the range of this. So let's say I wanted to integrate this from -2 to 2 instead. I could just move this slider out to a 2 there, move this slider out to a -2. You've got 2 dots there for controlling the left and right bounds. So from -2 to 2, I'm guessing that's supposed to be 5 1/3, it looks like. And so this is what you can do to take the integral of any function that you want, right? We started with one we knew the answer to. Let's try one we don't know the answer to. Let's try e to the sine of x squared. I don't care what your grade was in Calculus 2. You cannot carry out that integral, right? This is not something that we know the answer to. I mean, look at this thing. It's a mess. Again, you can play around with the dx. This time we don't know what the answer is, so I'm going to decrease the dx until this answer stops changing appreciably. See here, I'm just alternating between a 3 and a 2 in the last decimal place. So that tells me that this step size is good enough. Again, from the graph, I can see that it's nice and smooth. So when you don't know the answer, you're looking for the graph to become nice and smooth, and you're looking for this answer to level out. And again, I can change the bounds, right? I can move this out to the right to get me more peaks out there. I can move this out to the left. This ought to be an even function. Cool. So again, you can change the range here. If you need to go beyond the maximum here, right, the maximum right now is 10. If you needed to go beyond that maximum, all you do is come up here to the slider and just change the maximum value here. That's all you have to do. So that's a quick introduction to numerical integration before we use it in our modern physics context. So let's suppose you have carried out the shooting method. You've got some values for your psi, your wave function. What do you do with it now? One of the most important things you do with psi is to calculate what's called an expectation value. Remember, in quantum mechanics, you can't ever know exactly where the particle is. You just have a probability distribution. But you can talk about the average value where you expect it to lie. So expectation value, basically a synonym for average value. If you were to repeat the same experiment many, many times, where would the average be of where you found the particle? Psi, the wave function, gives you the expectation value if you just follow a simple recipe. You take the integral over whatever your range was. In principle, this is supposed to be minus infinity to infinity. It could be minus 5 to 5. If that's the range you have your data over, then that's what you have to do the calculation over. What you do, you take the psi, you take its complex conjugate. We don't really have to worry about that because our size and our code are real numbers, so you can ignore the star if you want, but if I don't put it on there, I'll get angry comments on the video. You place the thing you want the expectation value of in the middle, put another psi over here, tack on a dx. Now this order does actually matter. We'll talk about why it matters in a couple minutes. Again, this is not something the computer can carry out because we don't have the function for psi. We have discrete values. So again, we turn this into a Riemann sum. We turn this into a summation over all of your values. So I is your value index from the code. All right, it's psi array bracket I, close bracket. You would take your psi array at I, your x array at I, your psi array at I, dx. Right? This is a thing we can carry out, right? This is a loop, right? This is just a loop. Multiply these things together, keep adding them together, and you'll get your expectation value. By the way, this requires your psi must be normalized. That's why we took that minute at the end of the last video to take a look at how we normalize psi, because without a normalized psi, this answer doesn't make any sense. And again, the thing that goes in the middle is whatever is inside the expectation value function. So if you're looking for the expectation value of x squared, you would have integral of psi star x squared psi dx. And again, that's just going to get replaced by a Riemann sum, psi I xi squared, psi I dx. Right, it's not the same, right? So it's not the same thing as taking this stepper and squaring it. So the expectation value of x squared is not the same thing as the expectation value of the square of x, right? And you'll see that when you work out the activity. The reason this order is important is because of what happens when you go to calculate the expectation value of momentum. So with x, the order doesn't really matter because it's just a number. But remember, in quantum mechanics, momentum is no longer a number. It is now an operator. It is, in fact, h bar over I, a derivative with respect to x. It's a set of instructions. So in other words, when you come over here, you're taking your integral of psi star. P is now h bar over I, d by dx acting on psi. So this is now telling you to take a derivative of psi with respect to x. So in terms of the Riemann sum here, this is h bar over I should have called this a j because our imaginary number is j, so pretend we've been calling these j's all along just so that you don't get confused, and I'm sure I'm just confusing you by changing them. It doesn't really matter what you call the number in the summation, right? It's what we call a dummy index. It doesn't actually impact the answer, it's just a thing to count it. So we got h bar over I here, summing over j. We'll have a psi j, and now I want to take psi prime at j times dx. And it's actually really handy because we have this stored in an array. Right? Because in the shooting method, you're updating psi prime in addition to psi. So we actually have this stored in an array, so we could actually go ahead and calculate this. Now, here's the trick with this momentum expectation value. For a stationary state like these psi's, this thing had better come out to be 0 because it has this I here, and I can't get an imaginary value for momentum. So for a stationary state, this thing had better come out to be 0. That's why we call it stationary, right? The other thing you're usually interested in is expectation value of p squared. So this would be integral of psi star. Let's see, if p is this, then p squared is going to be p times p is going to be an h bar over I d by dx, acting on h bar over I d by dx. Let's see, so I'll have an h bar squared. I times I gives you -1 by definition. And then a derivative on a derivative is just a second derivative. Interesting. So in other words, this is going to have a negative h bar squared, and then this is going to have a psi double prime. It's going to be d squared psi dx squared dx. Right? So this, in terms of Riemann sum, is going to be negative h bar squared, sum on j, psi double prime j dx. And again, we have this, right? We can either make an array for it, or we can go back and recalculate this at each point I, or each point j, because we have this. We have an equation for this thing. This thing is allowed to be bigger than 0. It's just this product, this sum of this product needs to come out to be negative to cancel this negative so that the whole thing is positive. But this thing's allowed to be bigger than 0. This is actually really important because this is the thing that gives you the kinetic energy. Because if you want the kinetic energy, that's equal to p squared over 2m. So you can take this value to get the expectation value of the kinetic energy.
So let's take a look at how this numerical integration works for the expectation values. At the beginning is a reminder of everything we talked about on the board. Here's our transformation to a Riemann sum, and here's how we actually do this. First, we're going to repeat everything we did with the shooting method because I actually need the array of psi values here. So we're going to start out by rerunning our code for the shooting method. So you already got the energy eigenvalues that you need here. So you just take your energy eigenvalues from the shooting method activity that you completed and put in each of those here for your wave function. You should get the same wave function graph you had before. Then we're going to run this code to calculate expectation value of x. First, we'll normalize the values of psi and the values for, So first, we'll normalize the values of psi, just like we've done before. And then we'll calculate the expectation value of x. And this is, for all the buildup we've had, numerical integration is actually really simple in terms of writing the code. You need some kind of total, right? You need a value for the integral. That is our expectation value of x. We're going to call that expectation x. Start out with that equal to 0. Anytime you're adding a bunch of stuff together, you have to start at 0 as your baseline. Then you're going to loop over all the values. So whenever you have a summation in the equation, it becomes a loop in the code. So that sum over I is now a loop over I. So we've got for I in range, length of x arrays, it's going to loop over all the values of I. And it's say expectation value of x equals the previous value. So we're taking the previous value we had and we're adding to that. So it's just going to get bigger. This thing is only going to add together. We take psi array of I times x array times psi array of I again. And don't forget to multiply by that dx because that is an important piece. It's not just a thing for the calculus to work. In a code, that step size is an actual numerical value. So this is the thing we had inside the integral, right? Psi x psi dx. In the integral, you had psi x psi dx. And then we'll print the expectation value. What I hope you'll notice is that this expectation value comes out pretty close to 2. This is where you have to eyeball the results because there's always going to be a little bit of truncation error, of rounding error at the end there. So usually if it's a number 0.00 and then some change, you generally want to ignore the change, right? What I noticed is special about this is that this 2 is right in the middle of the well. In other words, my expectation value for the infinite square well is going to be right in the middle. That kind of makes sense, right? On average, it should be, I mean, it has an equal probability of being just about anywhere, so it might as well, no, that's not true, excuse me. Right? It's got a symmetric probability across the left side and the right side, so it's going to average out to being in the middle, which is pretty cool. Your next goal is to identify how to do this for the expectation value of x squared. You'll just copy this little code snippet here and change this x into an x squared. Pretty straightforward. Then comes the part for the momentum where you have to take the derivatives. So this is where you're going to have to actually go back up to the shooting method here. As remember, you are calculating psi prime, so that is information that you have. So what you'll do here is add an array to calculate psi prime, or not to calculate, to store psi prime. And then what you can do farther down here is set up your expectation value, and the difference is going to be now, instead of having, what do we have up here? Instead of having psi array, x array, psi array, you're going to have psi prime array, and then psi array, nothing in the middle. Again, it's whatever's inside the integrand is what goes into your expectation value calculation. So you have your psi, and then you have your psi prime. Oh, I suppose you do need an h bar. Now, you'll probably be tempted to include this I. You can include that imaginary number if you want, but remember, for a stationary state, this thing had better come out to be 0 because you can't have an imaginary expectation value of momentum. P squared, fair game. You throw in this negative h bar squared, this integral will come out to be negative to cancel this negative, and you'll get a nice positive value for expectation value of p squared there. And the best part is you can do this, you can use this machinery for any problem. So we're going to start out with the infinite square well, then you can move on to the harmonic oscillator there and get its expectation values as well.